Did you know that the universe is not only expanding but doing so at an accelerating pace? That's right, folks. This isn't just some cosmic fairy tale. It's hard scientific fact, and it's one that's been turning our understanding of the universe on its head for a good few decades now. You see, it all started back in the 1920s when Edwin Hubble, that's right, the man after whom the Hubble Space Telescope is named, made a groundbreaking discovery. He noticed that galaxies were moving away from each other. The universe, he realized, was expanding. But it wasn't until the late 20th century that scientists discovered something even more mind-boggling. The universe wasn't just expanding, it was doing so at an accelerating pace. Now, this revelation posed a major challenge to our understanding of the cosmos. According to the laws of physics, the universe's expansion should be slowing down due to gravity, not speeding up. So what could be causing this cosmic acceleration? Enter the concept of dark energy. Dark energy, in essence, is a hypothetical form of energy that permeates all of space and exerts a negative pressure, driving the universe to expand at an ever-increasing rate. It's believed to make up about 70% of the energy in the universe, yet it remains one of the greatest mysteries in modern astrophysics. We can't see it, we can't touch it, but we can observe its effects on the universe's expansion. So, here we are in a universe that's not only bigger than we ever imagined, but also expanding faster than we ever thought possible. It's a universe full of mysteries, full of secrets waiting to be unraveled. And the biggest secret of all, how it all began. So, let's dive into the enigma of our universe, starting from its very birth, the Big Bang. Imagine a time before the Big Bang when there was nothing, no stars, no galaxies, just absolute nothingness. This is the concept of singularity, a point at which all the laws of physics as we know them cease to be applicable. This is where it gets interesting, folks. The singularity is thought to have contained all the mass and spatial dimensions of the universe, condensed into an infinitesimally small point of infinite density. Hard to wrap your head around, right? It's like trying to imagine a dot that contains everything you know and don't know. Now, some theories suggest that before the Big Bang, our universe was contracting rather than expanding. It's as if you took a movie of the universe's expansion and played it backward. This is known as the Big Bounce theory. According to this theory, our universe is just one phase in an infinite sequence of cosmic expansions and contractions, like the rhythmic breath of some gigantic cosmic entity. Then there's the idea of a multiverse. This isn't a concept out of a sci-fi novel, but a serious proposition in cosmology. The multiverse theory suggests that our universe may be just one of countless others, each with its own laws of physics. Some might be similar to ours, others radically different. So, before our Big Bang, there may have been other universes, other Big Bangs. These theories are all intriguing, but remember, they are just theories. They represent our best attempts to understand what came before the beginning of everything we know. It's a bit like trying to read a book when you're only allowed to start from chapter 2. But then, in an instant, everything changed. The Big Bang happened, and from that moment on, we started to have a universe that we could begin to understand. But that's a story for another scene. In a fraction of a second, the universe was born from the singularity, exploding into existence. Picture it as the ultimate firework display, a symphony of cosmic creation that began with a single infinitesimal point. This was the Big Bang, the moment when everything we know, space, time, matter, burst forth from an entity so tiny and yet so dense, we can hardly wrap our minds around it. But this was no ordinary explosion. It wasn't an event taking place in space, but rather, it was the creation of space itself. And so began the grand ballet of cosmic inflation, an era of rapid expansion that lasted a minuscule fraction of a second. In this fleeting moment, the universe expanded faster than the speed of light, growing from a size smaller than an atom to an astronomical expanse. But even as the universe ballooned in size, it was still a hot, dense sea of energy. It was too hot for matter to exist. But as the universe continued to cool and expand, something phenomenal happened. The energy began to condense into particles. First came the quarks and then the leptons. These particles were the building blocks of matter, the seeds from which everything we know would eventually grow. As the universe cooled further, these particles began to combine, forming the first atoms. Hydrogen and helium, the simplest and lightest elements, were the first to form. They were the first to light up the universe, breaking the cosmic darkness. And then, for the first time, light was born. The universe was no longer a dense fog through which light could not travel, but a cosmic stage where light could dance and twirl. This light, the cosmic microwave background radiation, is still visible today, a testament to the universe's fiery birth. From this chaotic beginning, the universe as we know it began to take shape, from a single point of unimaginable density to a vast, ever-expanding cosmos. The birth of the universe is a tale of creation like no other. It's a story that continues to unfold as we, the children of the stars, seek to understand our cosmic origins. Over billions of years, the universe evolved from a hot, dense state to the vast expanse we see today. This transformation is a tale of creation and destruction, a cosmic drama unfolding over epochs and light years. In the early universe, matter and energy were uniformly distributed. Then, under the relentless pull of gravity, matter began to clump together. These clumps grew denser and hotter until they ignited, sparking into the first stars. These stars were nothing short of cosmic factories, forging lighter elements like hydrogen and helium into heavier ones like carbon and oxygen. These first stars lived fast and died young. In their explosive deaths known as supernovae, they spewed their freshly made elements out into space. This stardust, enriched with the building blocks of planets and life, would eventually coalesce to form new stars and planetary systems. Over time, the universe became a cosmic web of galaxies, each a bustling metropolis of billions of stars, linked by dark matter and crisscrossed by the light of ancient supernovae. Some galaxies, like our own Milky Way, gave birth to planets with the right conditions for life. On one such planet, Earth, the elements forged in the hearts of stars came together to create life. Life that evolved over billions of years into us. We are, in a very real sense, star stuff. And so the cycle continues. Stars are still forming and dying, creating and dispersing elements. Galaxies continue to collide and merge, shaping the large-scale structure of the universe. In the grand scheme of things, we are a blink in the cosmic timeline. Yet we are the universe's way of understanding itself. We have the ability to look up at the night sky, to see the light of distant stars and galaxies, and to ask questions about where we came from and where we are going. And here we are, a tiny part of this vast cosmos looking back and trying to understand our origins. Now, what does the future hold for our universe? As we gaze into the cosmos, we can't help but wonder about the destiny of the universe. Theories abound, each as captivating as the next. Two of the most compelling theories are the Big Freeze and the Big Crunch. Let's start with the Big Freeze. This theory is based on the observation that our universe is not only expanding, but doing so at an accelerating pace. If this trend continues unabated, the universe's temperature will gradually decline as its energy disperses. Over trillions of years, stars will exhaust their nuclear fuel, galaxies will drift apart, and eventually, all matter will decay to an ultra-low energy state. The universe will become a vast, dark, and cold place, hence the term Big Freeze. On the other hand, the Big Crunch theory paints a different picture. This theory posits that the expansion of the universe could one day reverse, causing all matter in space to collapse in on itself. This would lead to an intense concentration of energy and matter, resulting in a crunch. It's like rewinding the Big Bang, culminating in a singularity. But what role does the accelerating expansion of the universe play in these theories? If the expansion is indeed accelerating, it lends more credence to the Big Freeze scenario. However, if dark energy, the mysterious force driving this acceleration, were to weaken or reverse, the Big Crunch could come into play. It's fascinating to ponder these cosmic possibilities, yet it's humbling to remember our place in the grand scheme of things. We are but fleeting observers in the cosmic timeline, born from the remnants of ancient stars. Our understanding of the universe is constantly evolving, much like the universe itself. As Carl Sagan once said, the cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. And so, as we strive to comprehend the future of our universe, we are in essence trying to understand ourselves.